about specific heat. Now, hopefully you learned in your notes that specific heat is the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. And honestly, that definition is written in the units. The amount of heat required to raise the temperature of 1 gram by 1 degree Celsius. So it's joules per gram degree Celsius. Now, if you don't remember that unit, it is on your reference tables because the specific heat of water is there. But I want you to notice the specific heat of water changes based on which phase of matter it is. If it's ice, it's 2.05. If it's gas, it's 2.02. And if it's liquid water, it's 4.18. Ooh, there's that 4.18. Do you remember 4.184 is your conversion from joules to calories? So that even though you have to not memorize that 4.184, the specific heat of water is that same value. So that's kind of nice. Okay, so when do we know to use specific heat versus the phase changes? You've got to think about what's going on with the substance. Is it boiling? Is it melting? Is it just changing temperature? If it is just changing temperature, you're going to be looking at specific heat. I do want to talk about two values. First of all, your reference tables doesn't just have the specific heat of water, it also has the specific heat of a ton of metals. So let's look at copper versus water. Okay, think about these two substances. Which one is easier to get it to increase its temperature? Think about it. Which one would feel colder faster if we put it in the fridge? Which one would get warmer faster if we put it on the stove? Wouldn't you agree that metals tend to heat up faster and cool down faster than water would? That's because water has a higher specific heat, has a specific heat of 4.18 joules per gram degree Celsius. Whereas copper, from our reference table, says it's 0.385 joules per gram degree Celsius. The higher the specific heat, the harder it is to actually heat it up. The higher the number, the harder it is to heat up a substance because it requires more heat to raise the temperature of 1 gram by 1 degree. Whereas this one takes less heat to raise the temperature. So keep that in mind. The higher the specific heat, the more difficult it is to actually raise its temperature. Here's your formula, and I do want to make sure that not only do you get the formula written in your notes, but you also get copied what each letter means. And this formula is in your reference table. It's on the formula sheet. MC delta T, yeah, MC, and it actually uses a capital C with the subscript P. I usually don't include that in there, but definitely your reference table does, so make sure you recognize that as the same thing. M stands for mass. That's in unit grams. The C stands for the specific heat. So that's where we're going to put our constant in. And then T, delta T, remember delta means change in. So the change in heat means the change in temperature, and you do need to know that that means the final minus initial. Final temperature minus initial temperature. Make sure you know that part, okay? Now, before you can just use this formula, you have to double check if the problem's actually asking for a change in temperature, or is it going through a phase change? You're going to have to figure out which one to use. How much heat is lost when 4,110 grams of aluminum cools from 660 to 25? How much heat is lost? Okay, first of all, that answer tells us what our final answer should have. Our lost means it's losing heat. Heat is going down. That means that our final answer should give us a negative number. 4,110 is our mass. Okay, there's our mass of aluminum. So that tells us our substance. That's where we're going to get our specific heat from. And here is our from 660. There's our initial temperature. And here's our final temperature. Okay? So we see that temperature is changing. Therefore, we're going to use Q equals MC delta T. What I said is the hardest thing about these problems is actually determining your formula. Be thinking, is this a phase change? Is this a temperature change? Got to be thinking about what's actually going on. So Q we're trying to find. M is 4,110 grams. C is our specific heat. Now we're going to have to look it up, so grab your reference tables. We're looking at aluminum. The specific heat for aluminum is 0.897 joules per gram degrees Celsius. And delta T is the final temperature minus the initial. So it's actually going to be 25 minus 660. Okay? And that is negative 635. And that is degrees Celsius. So there you go. Hey, our final answer should be negative. If you do your temperature calculations properly, you're going to get a negative number there. So that will work out nicely for you if you're thinking about it. It's a good way to check your work. So now let's solve for Q. Mass is 4,110. Specific heat is 0.897. And our change in temperature is a negative 635. So that's multiplied across. Go ahead and grab your calculators. And we're going to do 4,110 times 0.897 times a negative 635. And I get negative 2,0341035 joules. And let's add some commas in there so we can make sense of that. That's an acceptable answer for academic folks. Honors, you're going to have to think about sig figs here. When we subtract these, we've got to go to the placement. So it's 25 minus 660 dot, so that's 635, good. We're going to the ones here. Don't lose sig figs because of a constant. So we're looking at 3 sig figs, 3 sig figs. Final answer should have 3. That's going to be right here. That's 2, 3, 4, 0, 0, 0, 0. There it is for honors, folks, negative still. Definitely can convert that to kilojoules if you'd like. Again, academic, cool, this is an acceptable answer. Honors, in order to get all your points, you need to make sure you think about sig figs. Okay, calculate the heat required to heat up 124 grams of water from 17.5 to 45.8. Okay, first of all, required. That means we need to add heat. Our final answer should be positive. We look here and we see that the temperature is changing. That tells us that this is going to be a specific heat problem. So we're going to do Q equals MC delta T. It's going to give us a positive answer. We are talking about water here. You got to think, in this temperature, what phase of matter would water be in? Water melts at 0 and boils at 100, so it's definitely going to be a liquid here. So therefore, we can use C is going to be that 4.18 from our reference tables. And M is 124. And delta T is going to be 45.8 minus 17.5. And I'll go ahead and double check that in my calculator. 45.8 minus 17.5. We get 28.3 degrees Celsius. Notice, final temperature minus initial is going to give us that positive number here. We want a positive number in the end, so that's a good way to check that we're doing things accurately. At this point, it's a plug and chug. The hardest thing is figuring out which formula to use, but once you figure out the formula, it is a simple plug and chug. The math is not hard. You've just got to get those concepts straight between heat of vaporization, heat of fusion for phase changes versus specific heat for temperature changes. So we've got 124 grams times the specific heat, which is 4.18, times your change in temperature, which is our 28.3. And when we multiply those, honors folks, we should have 3 sig figs. We get 14,668 joules. Academic, that's a beautiful answer for you. But I do want to talk to my honors folks about sig figs. There should just be 3 because our temperature after tenths, do think about subtracting the temperatures properly. We should have our final answer to the tenths. This is 3 sig figs. Don't pay attention to constants. This is 3 sig figs, so our final answer should have 3. That's going to be 14,700 joules. That's what I'm assuming honors folks really should be expected to write. Okay? Academic folks, please do not freak out about this. You don't even need to worry about it at all. So here's our honors answer. And here's our academic answer, just to make sure we're all on the same page. So before I moved on from this video, I wanted to make sure I summarized the 3 things that you really need to know about how to do these calculations. The math is not very tricky. It's just a matter of knowing which formula to use, keeping all your constants straight. So I really wanted to take some time to summarize these. So specific heat is all about temperature changes. I also would suggest that you write this down somewhere in your notes. I don't think there's an actual spot in your note packets, but I want to make sure you get this written down. So when you read the problem, gotta ask, is the temperature staying constant or is the temperature changing? If the temperature is changing, then you've got to use the specific heat formula, which is Q equals MC, because specific heat is a capital C, delta T. And you can get the specific heat value from your reference table. Everything else should be given. But we've got these other 2. Heat of fusion, if both of these are for phase changes, that means if it's boiling, melting, freezing, condensing, something like that. Heat of fusion is specifically for melting and freezing. Remember, melting is going to be endothermic, freezing is going to be exothermic. And our formula would be Q equals M delta H of fusion. Notice temperature isn't in this formula at all. Why? Because temperature stays constant during phase changes. Heat of vaporization is another phase change, boiling or condensing. It tends to give us much larger values because it requires more energy to do those phase changes. And these abbreviations, delta H, fusion, delta H, vaporization. We come over here, the formula for this, Q equals M delta H of vaporization. Again, remember, during the phase changes, we don't have any temperature in those formulas because temperature is staying constant throughout the phase changes. So there's a summary of all of them. Go back through your homework, go back through your notes, make sure you're able to identify which equation you're supposed to use on which type of problem, and it's all based on what's actually happening. And again, boiling is going to be endothermic, condensing is going to be exothermic. Practice those phase changes as well, and if they're endothermic or exothermic, make sure you know that. So here we are with heat calculations using specific heat for temperature changes, the heat of fusion and vaporization for phase changes. Thank you.